The main difference between solids, liquids, and gases is their intermolecular forces. As you know, intermolecular forces are the forces that attract molecules to each other. Also, solids, liquids, and gases are different because of how close their particles are to each other. Let's turn to Catherine to find out more about the properties of solids, liquids, and gases.
Solids have the strongest IMFs of all states of matter. Because of this, it takes more energy to pull molecules apart from each other to be in a gas or liquid form, so solids have very high boiling and melting points. Believe it or not, like liquid and gas particles, solid particles are always moving. The chair you're sitting in right now has moving particles. However, the particles move so slightly and are so close together that you can't feel it. Solids don't flow. Imagine trying to pour out a cup of ice. The ice does not smoothly flow out, it rather falls out of the cup. Liquids have the next strongest IMFs. Liquid particles have moderately high melting and boiling points because their intermolecular forces are weaker than solids. However, particles are still pretty close to each other, but they're able to move past each other and flow. Gases have the weakest IMFs of all. Gas particles can spread out very far and move very quickly around each other with very high kinetic energy. Due to their weak IMFs, gases have low boiling points and high melting points. So, to recap, stronger IMFs equals higher boiling points equals less movement of particles. Let's help you understand how particles of solids, liquids, and gases are related to each other. First, we'll show you what solid particles look like. As you can see, these particles are very close to each other, but can still move. Now, we'll show you what liquid particles look like. They spread out a lot more, but are still pretty contained. Lastly, here's what a gas looks like. These particles have a lot of energy and move very quickly and far apart from each other. As you can see here, a solid does not take the shape of its container or the volume, and as you pour it into another container, it will not take the shape of that container either.
We have water in the beaker, and as you can see, it's 200 milliliters. When you pour it into here, the liquid flows and takes the shape of this container, but it's still 200 milliliters.
Here we have a beaker representing gas. When you pour the gas into this container, it takes the shape and volume of this container.
We're going to talk about exothermic and endothermic processes. An exothermic process is when a solution releases heat. In the name, there's exo. Exo is like exit. The heat is exiting the solution. Some exothermic processes are freezing, condensation, and deposition. Deposition is when a gas goes straight to a solid without becoming a liquid. An example is when water vapor in the air becomes solid in snow.
Endothermic is a process where it takes in the energy from outside. Endo means in, so it's taking in energy. Some examples are melting, vaporization, and sublimation. Dry ice is an example of sublimation because it's a solid turning into a gas.
Here, we have a solid and a liquid. Although they look different, they'll be the same soon. Let's take away heat and see what happens. Let's go check on that liquid we put in the freezer. Holy moly! It's a solid! When we put the liquid in the freezer, it lost energy. The loss of energy caused the particles to stop moving as fast, therefore becoming closer together with stronger IMFs and becoming a solid. This is an exothermic reaction called freezing.
This ice cube is melting. It's an endothermic process because when we took it out of the freezer, the air on the outside is warmer than the air inside the freezer. So therefore, the molecules are moving faster and the solid is melting.
Boiling water is the opposite process of freezing water. Instead of removing energy, we are now adding energy in the form of heat. The molecules begin to speed up and move so fast that they begin to turn into a gas. The bubbles are the gas that it's forming. This is an endothermic process.
We just took the speaker off the hot plate. The hot plate is much hotter than the air is in this room, so now the energy is being released and the water vapor is becoming a liquid again on the sides of the container. This is an exothermic process called condensation. It is important to understand how there are two ways that a liquid can form into a gas. Before I explain that, let me explain something called vapor pressure. By definition, vapor pressure is the measure of force exerted by the particles that vaporize from the liquid and collide with each other as particles above the surface of the liquid.
What?
Let's put that into actual English. State changes are always happening. Particles are always evaporating or leaving the surface of a liquid and becoming a gas. The pressure this gas exerts back in the solution is called vapor pressure. Vapor pressure increases with temperature because as particles gain more kinetic energy, it is easier for them to escape the surface of the liquid and exert pressure back on the solution.
A vapor is a fancy word for a gas. There's two types of vaporization, evaporation and boiling. Evaporation is when molecules with the highest energy are able to escape from the liquid and become gas particles. Boiling, on the other hand, is when a high enough temperature or heat is applied to the liquid, allowing all of the molecules to be able to escape. Boiling point is when the vapor pressure is equal to the atmospheric pressure.
Let's think of a phase diagram as a path. To help explain this path, Mia and Caitlin are here to help. As you can see, Mia and Caitlin are standing in the bottom left-hand corner of our chart. They are standing very close together, representing a solid. Now, as they walk up the diagonal line, the temperature is increasing. Once they come to the first horizontal line, they are now in the process of melting and are beginning to move farther apart from one another. As they go up the second diagonal line, they are now a liquid. The temperature continues to increase, and when they get to the second horizontal line, they are now in the process of evaporation. They are gaining energy and moving very far apart from one another. Now, as Mia and Caitlin move up the final diagonal line, they are a gas. Heating and cooling curves are special because they can be used forwards and backwards. This time, Mia and Caitlin will be standing at the top right-hand corner of the chart, representing a gas. As they move down the chart and approach the first horizontal line, the substance loses energy. These gas particles are in the process of condensation. As they continue down the second diagonal, they now represent a liquid. The second horizontal line represents the process of freezing, going from a liquid to a solid. The particles are now slowing down significantly as they are losing energy. By the time they reach the final diagonal line, they are now a solid. To summarize, these curves are helpful because they show the relationship between the state of matter and the temperature at which they occur. On the flat part of the curve, potential energy is used to separate particles and change their phase. On the diagonal parts of the curve, kinetic energy is used to increase the temperature of the substance.
This is a vapor pressure curve. A vapor pressure curve shows vapor pressure versus temperature. Now, before, we said that the boiling point is when the vapor pressure equals the atmospheric pressure. At 1 atm, we can go across the graph and see that water has a boiling point of 100 degrees Celsius. Now, different substances have different molecular makeups and also different IMF forces, causing them to have different boiling points. If we look at substance X, at 1 atmosphere, instead of having 100 degree Celsius boiling point, it's a little bit greater. This is a phase diagram. A phase diagram is a graph showing the relationship between the temperature and pressure at each state of matter. Across the x-axis is temperature. Going up and down the y-axis is pressure. Here is the triple point. At the triple point, all states of matter exist at equilibrium. That means solid, liquid, and gas. Here is the critical point, which is defined by the critical temperature and the critical pressure. The critical temperature is the temperature at which a gas cannot be condensed into a liquid, no matter how high the pressure is. So above the critical point, it's always a gas and can never be a liquid. At the critical pressure, it defines the pressure required to liquefy a gas at the critical temperature. Each line is the border between the different states. At this line, there is a border between solid and liquid. Right at this line, both solids and liquids are at equilibrium. Also, since this is a phase diagram for water, a solid for water, which is ice, is much less dense than the liquid form of water, which is just water. Therefore, this line or border between the solid and liquid has a negative slope. If the density of the solid is greater than the density of the liquid, the border will have a positive slope and go this way. This border is a border between liquid and gas. Therefore, at the border, both liquids and gases are at equilibrium.
Matters changing. It could be fast or slow, going up the curve. From solid to gas, you know.